excited to have Jon Arrizabalaga with us. Jon joins us from the Technical University of Munich, and Jon's a PhD student at the Munich Institute of Robotics and Machine Learning or Machine Intelligence at TUM under the supervision of Markus Reil. Since Jan 2024, Jon is also located at the Robotics Institute at CMU, advised by Professor Zachary Manchester. Before pursuing Jon's doctoral studies, he obtained his MSc degree in robotics mechatronics at KTH Royal Institute of Technology in Sweden and wrote his MSc thesis at the robotics department of Bosch Research in Germany. Jon's research interests lie at the intersection of system dynamics, control theory, numerical optimization, and machine learning, with a special focus on their applications to robotic and autonomous systems. More specifically, his work aims to enhance the agility, efficiency, and robustness of such systems by developing novel methods that unify perception, planning, and control in a transparent and understandable manner. I'm really excited to hear Jon talk, as I'm sure all of you are. So I'm going to stop sharing my screen. And Jon, please feel free to take it away.
Okay. So thank you very much for the introduction, Nivi. That was wonderful. And thank you very much to all the organizers for letting me present my work here in this great seminar. It's amazing, this initiative you've got, that you give a voice to everyone. I really like it. And for that, I'm thankful. So my talk goes under the name Egocentric Decision Making for Robot Autonomy. And to motivate this talk, I thought there was no better way than to show videos of a cheetah doing its own thing in the nature, in its own habitat, running and kind of jumping around. Cheetahs are the fastest animals on Earth. They reach a maximum speed of 115 kilometers per hour, and they can do this within a time window of 3 seconds. And the reason I'm showing these videos is because these cheetahs kind of embody what we would like to have with our robotic systems, the agility, the performance, and the adaptability that we would really like to mimic in our robots. We have to confess that our robotic systems are not there yet. We've got a gap between these current cheetahs and our existing robotic and autonomous systems. And basically our daily lives as researchers are all about kind of trying to close this gap. However, we are getting closer and closer, and in the last recent decades, we've done some major progress towards closing this gap. And to motivate my talk, I've collected 3 different examples that kind of illustrate where robotics today stands and what's the current location of robotics and which are maybe the specific points that we need to be addressed. And I will use these 3 examples as somehow the motivation for the content that I will outline in this talk. So the first example regards the Subterranean Challenge, the SubT Challenge, which took place between 2018 and 2021. The goal here was that a fleet of robots would have to identify different objects that were located in underground environments, such as caves or tunnels. There is no doubt that this challenge, it's well known among the roboticists, and it was kind of a success because it advanced the field in robotics and in multiple domains or subfields of robotics. However, despite these challenges and the amazing performance of all the participants, we cannot forget that no team was able to find all the objects. In fact, the winning team won by finding 23 objects out of the 40 that the organizers located in this environment. And the point that I want to make through with this example is that there is a gap between what the organizers consider to be excellent performance and what actually the robotic systems could do. The second example I wanted to talk about, of course, is autonomous driving. We've been promised that autonomous cars will get to our roads for over a decade now, and definitely we know that this is still not true. If we check the numbers provided by one of the best services of autonomous driving out there, from Waymo, they claim that they've got over 25 million miles of autonomous driving, which definitely it's a lot, and it's a major success being able to accomplish such a big mileage. To do this, they rely on high definition maps or HD maps, which usually require centimeter level accuracy. So thanks to these HD maps, they are able to somehow report such a big mileage. However, these HD maps also imply that they are only providing their services in 5 cities. What I'm trying to say here is that due to the reliance on these HD maps, they are struggling to somehow provide their services in other environments or other cities and kind of provide the universal autonomous driving pitch that they've been promising. And the last example that I want to talk about takes us to Mars. What you are seeing in the left-hand side is the Curiosity rover, which is a robot that has been deployed in Mars for 11 years. Arguably, this is one of the most successful deployments of robotics ever made. This robot is extremely complicated. It has the most advanced instruments and it's doing actual super cool research. And it has been doing this for 11 years, which in the harshest environments we can imagine, such as the Red Planet. If we look into how much distance it has covered in this time, we see that that's 31 kilometers. And that might seem like a lot, like a big distance. But we kind of realize as soon as we divide these two numbers, that adds up to roughly 8 meters per day. So the Curiosity rover, the maximum distance that it got to cover in one day was 8 meters per day. The reason for this is that every time the Curiosity rover would bump into a tricky scenario, the engineers in JPL would have to replicate this scenario in the Mars yard. And that's what you see here in the right-hand side of the slide. So somehow this approach where we've got engineers in the loop or the Mars yard in the loop implies or really limits the actual coverage the Curiosity rover could have and somehow compromises the science we can do on Mars. So if we take a step back, we've started this talk saying that this is what we want. We want our robotic and autonomous systems to have the agility, the performance, and the adaptability of cheetahs and actual animals. But what we've got, it's a bit more limited in the sense that we are making great progress. We are getting there, but our current robotic and autonomous systems kind of show a gap with respect to what we actually want. So in a nutshell, key message here that there is a gap between what we want and what we have. So of course, there are different reasons on how to address this gap and the reasons underlying this gap. And the most obvious one would be hardware. Here, however, I want to take another perspective on this, which is the fact that there are also some inherent differences on decision making. So the question I want to address here is, how do biological and robotic decision making differ? Once again, there are multiple answers to this question. Depending on who you ask, they might give a different answer. What I want to kind of convey in here in this talk, it's a very specific perspective, which is usually ignored in the robotics community. To convey this, I want you to look into this video where we see a cheetah hunting antelopes. And we see that in contrast to the previous examples, the cheetah does not reconstruct a world map and does not rely on a world map to take its decisions. It's taking its own decisions from its own subjective relative viewpoint. And if you think about it, we humans, we do exactly the same. All the actions we take, name it cooking, texting someone, working on our laptops, doing sports, everything we do is from our own subjective first-person viewpoint. However, as I was saying, sorry for that. However, as I was saying, in the robotic examples that I've just shown, usually what we do is we rely on our sensor, we reconstruct a world map, and we use this world map somehow to do the decisions or to take the decisions. So in other words, biology is egocentric, while robotics is allocentric. And this discrepancy is exactly what I want to address in this talk. So what I want to do with this talk is I want to lay the foundations so that we can bring the tools required to adopt egocentricity in robotics and autonomous systems. In other words, with this talk and with the work that I'm about to explain, I aim to answer this research question. How can we embrace egocentricity in autonomous decision making? So today's talk will evolve around this question. Before I get into the methods and the ingredients that I want to propose and show you to really answer this question, what I would like to do is I would like us to spend some time sanity checking our egocentricity hypothesis. In other words, I want to focus in validating the fact that embracing egocentricity actually makes sense. In other words, should we at all embrace egocentricity for autonomous decision making? So we will spend some time answering this question. This will allow us to validate our hypothesis, and then we will get back to our original research question. So to validate our hypothesis or to answer this modified question, we will focus on a very specific subproblem. And this problem is the time optimal tunnel following for quadrotors problem. We've chosen this problem for three main reasons. And before I get to uh, talk about these reasons, I want to clarify that this is a very specific problem. And we will use it as a test bed, as a case study, to really validate the validity of our hypothesis. That's our goal. So as I was saying, this problem, super specific, and we've chosen it for three different reasons. First of all, we are aiming for time optimality because we want to see if the egocentric paradigm allows us to embrace somehow the agility and the aggressiveness that we want for our robotic systems. Second, and it's the most important reason, we are doing this from a tunnel following perspective. This means that we mimic the egocentric perspective, we mimic the first person viewpoint through a tunnel. This tunnel represents this viewpoint that we usually animals and humans have. And what we will do is we will build an algorithm which is going to search for the optimal trajectories within this tunnel. So this is the second reason. And the third reason is that we select quadrotors as a platform because quadrotors are extremely agile platforms that evolve in the three-dimensional space. And this three-dimensional space, it's more complicated and shows some of the difficulties that ground vehicles like autonomous driving or other planar vehicles do not show. So here we are able to really observe the most generic setup of the problem. So to do this, we will, let's say, given that this is just a fast sanity check of our hypothesis, I don't want to go down every specific details and to bore you with all the details of how we actually solve this. I want you only to keep in mind that the method to solve this problem had two main ingredients. The first one was that we project our quadrotor system dynamics to the center of the tunnel. So what we do is, I hope you are seeing my pointer, my marker here. What we do is we project the system dynamics into the center of the tunnel, and thereby we are able to operate with the spatial coordinates instead of the Euclidean or Cartesian coordinates. So having access to these spatial coordinates allows us to somehow exploit the geometry of the tunnel. So maybe this was a bit too, let's say, fast. What I want to clarify here is that the spatial coordinates are the progress along the path and the orthogonal distance to the center of the tunnel. And having explicit access to these coordinates will be extremely useful from a control theoretic or a planning perspective. So let's say, I will get into these details a bit further ahead, but that's the first ingredient. And the second ingredient, once again, don't get scared by the math, just stick to the concepts, is that we embrace this or we exploit these spatial coordinates by a non-linear model predictive controller, by an NMPC. So what we do here is we solve a small optimization problem at an iterative fashion, so at 50 Hertz, and through this small optimization problem, we are able to iteratively compute the trajectory within this tunnel. Once again, I'll not get into the details because we could do an entire talk about it. But yeah, the idea is that we solve the tunnel following problem and it underlies these two ingredients. And this will allow us to validate our hypothesis. To do that, basically to validate the hypothesis, we've conducted 3 experiments with this setup. So in the first experiment, what we did is the obvious thing of comparing the time optimality validity of our method. So our method is given in yellow, and the optimal solution, the theoretical optimal solution, is given in blue. What you see with the gray lines kind of depict the edges of the tunnel. And here the idea is that the time optimal theoretical solution requires up to an hour of computing. So it needs it's an offline solution, while our solution runs online and it doesn't require any offline computation. And what we see that basically we are extremely close to the theoretical bound, to the theoretical solution, and we are able to achieve this without any sort of offline compute in real time. So this kind of validates that embracing egocentricity, it's really pushing the capabilities of our dynamical systems to leverage the agility and the environment that we've got. In the second experiment, we kind of made sure that we were not overfitting, quote unquote, to that specific setup, and we changed the complexity of the tunnels. So we validated this in different tunnels for different initial conditions and different setups with some sort of randomization. And we saw that regardless of the tunnel's complexity, we could always guarantee this near-time optimal behavior. And in the third experiment, what we did is we wanted to see what would happen if the environment would be dynamic. So you can imagine that in certain scenarios, we are deploying our drones in a place where the environment is changing, either because there are moving obstacles, there are humans, there are other drones. So in that case, the tunnel would change. So the question is, if the tunnel changes, are we still able to keep ourselves within that tunnel? So that's what we addressed here. And I'll not get into the details, but we could see that regardless of how the tunnel was changing, we were able to stick ourselves to the constraints of the tunnel. And on top of that, another cool feature is that with exactly the same controller that we used for flight aggressive maneuvering, we are able to do stop and go and backward maneuvers without any tuning, off the shelf right away. So that's kind of like, at the time, it was kind of a big deal. So after these three, let's say three experiments, if we get back to our initial question, should we embrace egocentricity in autonomous decision making? I hope that after showing you these three experiments and this toy example, we kind of say that yes, egocentricity is worth being pursued, and we should try to kind of generalize it to the broader setup. So I hope that I've been able to convince you of this. So if we take this as granted, and hoping that you agree with me, now we are ready to go back to our original question. How can we embrace egocentricity in autonomous decision making? So the remaining of the talk will somehow address this question in a very careful and modular way. To do that, once again, I would like to get back to the tunnel following problem and kind of why I want to do this. I want to motivate the sub parts that we are going to be focusing on according to the example that I just showed you. Because the shortcuts that we've taken in order to make this example work are kind of also the reason why we are not able to extend this to the broader general setup. So I want to highlight these shortcuts, these limitations, and we will use this as a springboard to somehow outline the remaining of the talk. So the first limitation is that the projection of the Cartesian coordinates or the system dynamics of the quadrator to the center of the tunnel was system specific. We did this, we took the shortcut of doing it for a case study that was only applicable to the quadrators. So how can we generalize this? How can we do this? How can we do this for any moving point in space? Be an end effector, be another vehicle, right? That's the first question. The second limitation or shortcut we took is related also to the projection. This is something I've omitted so far, and we will get to in the upcoming slides. But in order to do this projection of the quadrator system dynamics to the center of the tunnel, we rely on a moving frame, on a frame that is attached to the center of the tunnel. And in order to make this possible for this work, we made a collection of tricks and hacks that would kind of dodge all the potential numerical issues that would come up. Of course, we didn't write this in the paper, no one does, but those hacks, those tricks, that cheating, quote unquote, it was there. So if we would like to kind of apply these projections to any given geometry, to any given setup, of course, we have to find a proper way to do this. So how do we parameterize the path? And the third question is probably the one that all of us are like wondering, which is the obvious thing that we are just using a tunnel as an environment representation. And if we would like to represent any environment, the tunnel is just too limiting by itself. So we don't have the capability to really express the richness of a obstacle-free space if we stick ourselves to a tunnel. So how can we come up with an environment representation that has enough expressiveness to represent any given environment while remaining computationally tractable? So we think, or at least I think, that addressing these three questions will be the key enabler to embracing, or at least allowing practitioners, robotic researchers, and other people to embrace egocentricity in decision making. And my belief is that due to the fact that we have not been able to answer these three questions, the egocentric decision making literature, it's a bit chaotic. So what I intend to do in this talk, in the remaining of the talk, is I will address each of these questions and somehow provide the required tools and hopefully answer the main question. So on that note, I think we are ready to start with the first question, which is how do we generalize the spatial representation to any dynamical system? To do that, I would like to start with the planar version, the two-dimensional version of the tunnel following problem, which is a car somehow driving on a road. So in this case, the car would be the two-dimensional version of the drone, and the road would be the two-dimensional version of the tunnel. So if we were to generalize this to any problem, instead of the car or instead of the drone, we would have a dynamical system. And the center line of the road or the center line of the tunnel would become a parametric path, which is given by a parametric function, denoted by gamma here. A parametric function means that it takes a path parameter psi here as input, and it outputs the center line of the road, so the x, y, z coordinates. So if we want somehow to have access to the spatial coordinates that we've already mentioned in tunnel following, if we want to have access to these coordinates, we have to augment the parametric path, the center line of the road, by a moving frame. This frame, it's a frame that is associated with the parametric path, and it's attached to the parametric path and somehow moves along the parametric path. And the idea is that it is also a parametric function, which means that we just need to provide it with the path parameter, and it will output the rotation matrix associated to the frame at any point in the road. So if we augment the parametric path with such an adapted frame, we immediately have the capacity to jump from the Euclidean coordinates to the spatial coordinates and vice versa. So just to be clear here, the spatial coordinates, once again, refer to the progress along the path and the orthogonal distance to the closest point in the path. So eta1 and eta2. And some of you might be wondering, why do we even care about the spatial coordinates? What's the entire deal of the spatial coordinates? Well, the idea is that from a planning and control perspective, if we've got access to these variables, we can somehow design behaviors that are geometrically very meaningful and very complex. However, if we just operate in the XYZ coordinate, we are somehow limited, and even sometimes the XYZ coordinates don't mean anything. So from a planning, decision-making, and control perspective, these spatial coordinates are extremely, they've got a very intrinsic great value. So if we want to use these spatial coordinates for decision-making, we gotta know, or we have to know how these spatial coordinates evolve on time. In other words, which are the equations of motion of these spatial coordinates? And the way in which we answer this first question of generalizing the spatial representation is exactly by doing this, by getting the equations of motion that describe the motion of these spatial coordinates. And this is how somehow we answer this first question. I'll not read somehow the text that is given in the box, but the idea is that these equations describe the equations of motion for the spatial coordinates for any parametric path for any adapted frame. I'll get into the kind of the conceptual benefits of these equations of motion in the next slide. Before I do that, I want to somehow shed some light into how we derived this. And there are two different ways to get into these equations. It could either be done through a kinematic approach, the same way we do in the mechanics course in undergrad, or we could do it from an optimality perspective. And no matter which path we take, we end up deriving these equations of motion for the spatial coordinates. So that's more in the mathy side. No, now, conceptually, why do we even care about this? So what's the deal with these equations? So the special attribute they've got is that, as I already said, they take no assumptions in the underlying adapted frame. So they are applicable to any moving frame. What do I mean with this? If we were to choose the most famous and well-known adapted frame out there, which is the Fresnel frame, and we would plug the equations of the Fresnel frame to our equations, we would immediately get the equations of motion which are specific to the Fresnel frame. And if some of you work on autonomous driving, you might immediately recognize these equations because they are all over the literature. So the point that I'm trying to kind of make through here is that these equations of motion are a more general setup that are applicable to any adapted frame and give the power to the user to decide which frame they want to use. Okay? So this is great, but here there is a small caveat or a small detail, and I would like to quote Uncle Ben from Spider-Man to do that, to kind of convey this message, which is that with great power comes great responsibility. These equations of motion are very powerful because they are very, very generic. But in this generality, it means that we've got the responsibility of picking an adapted frame. We have to choose the adapted frame. We've got the obligation to select which is the optimal relative or adapted frame. So this obviously raises the question, which frame do we pick, right? So let's say, before I move on to answering this second question, I want to conclude this first sub-question, which is that we've generalized the spatial representation through, basically we've generalized it through these equations of motion, and this has led us to questioning ourselves, how do we pick the frame, okay? So if we take this as granted, we've answered the first question, let's move on to the second question. So how do we parameterize any given path? Or in other words, how do we pick that frame, right? So before I suggest what I would do, or at least what we propose, I want to provide a brief overview of the options that we would have to provide a frame to the center line of the tunnel. So when doing this overview, I will analyze the existing methods from 3 different perspectives. I will evaluate them according to 3 different lenses. The first one is, are these frames singularity free, or do they somehow have numerical issues, and are they dependent on the geometry of the path? That's the first one. The second one is, we want the frame to be 2 times continuous, so the first 2 derivatives to be continuous, and we want to have the capacity to get gradient information. I can imagine that everyone understands the reason for this. The reason for this is that current decision-making processes rely either in optimization or learning, which require first and second order-based gradient information. So we need to have a frame whose gradient information is available. And the third reason, or the third evaluation criteria, it's going to be if they are simple. And the reason for this is it's the obvious thing that if things are way too complicated, people will just not use them. So simplicity, it's a good feature that we should aim for always. So the first option we've got for providing a frame, it's the Frenet frame. I've already talked about it. It's the most well-established frame out there, and it's the one that has somehow conquered the available literature. The reason for this is that the Frenet frame is analytically super simple, and in this simplicity, and because it's so lightweight, somehow people tend to use it very frequently. However, it shows some issues. So it has some singularities if the curvature vanishes. So if the path or the center line of the road becomes a straight line, the Frenet frame is not defined. And this also implies that it has its own, let's say, it is not continuous in the first and second gradient. An immediate response to this is the parallel transport frame, or the PTF. The PTF somehow provides a solution because it addresses the singularities of the Frenet frame, but it is not able to provide the gradient-based information that we need. And an interesting alternative to this would be the Euler-Rodriguez frame, or the ERF, which is singularity-free. It provides gradient-based information, but it's extremely complicated. So as an anecdote, myself, I was, for a big chunk of my PhD, I was a big believer on the ERFs, and I thought that they were the ultimate solution because they've got these nice mathematical properties. The thing is that conceptually they are so complicated that somehow they are an actual problem to become adopted by the broader community. I can provide way more details on this if you want offline, but there are like multiple reasons for this. So giving this, basically this was a portfolio of options that we've got, and kind of seeing this and seeing that none of the options would address all or tick all 3 boxes, we came up with a variant of the PTFs, what we call egocentric PTFs, which are a small tweak into how the PTFs are computed, which check all the boxes and provide us the adapted frame that we would need to use or to somehow to embrace egocentricity. So I hope that I've clarified our thought process and how we kind of ended up concluding with ePTFs. And once again, due to time constraints, I will not provide you explicit details on how these PTFs are computed, but we usually do this, or at least the algorithms that we came up with were 2 extremely simple algorithms that could be coded in 50 lines of Python. And somehow any undergrad would be able to code up easily. And that was our main focus, somehow ticking all the boxes, so being singularity free, C2, but most importantly, easy to implement so that they were lightweight. So I hope I didn't bore you down with this second question. I have to confess, maybe it's the less sexy point of the entire talk, but somehow it fully addresses the second question that we had. So in the first question, we talked about how to generalize the projections. Here we've talked about how to get those frames. And now we will move on to the third question, where we will talk about how to represent the environment. So we've already mentioned that if we would like to embrace egocentricity in generic environments, we cannot stick or limit ourselves to a tunnel-shaped thing. Usually, obstacle-free environments, they can take any sort of shape, and therefore we need to have enough expressiveness to represent this shape. So we came up with a method that somehow would address this need, and this method is a differentiable parametric corridor generator. So what it does, it's very simple. It takes the center line, the parametric path, the center line of the curve or of the tunnel, and a point cloud as inputs. The point cloud kind of represents the environment. And it outputs a corridor that is differentiable, it's continuous, collision-free, and parametric. And I will talk about why all these properties are interesting, but they are kind of like a nice to have for designing egocentric decision-making algorithms. So how this worked is that this method had three main ingredients. The first one was that we chose the corridor to have a cross-section which was an ellipse. This ellipse was allowed to change in the size, it was allowed to rotate, but it also had an offset with respect to the center of the tunnel. So it would be able somehow to shift its center position with respect to the, we'll say, the center line of the road. The second ingredient is that we somehow sweep the entire, let's say, parametric path or the center line of the road through Chebyshev polynomial. So what we do is we take the off-centered ellipse, we parameterize it as Chebyshev polynomials, and that way we are able to sweep that entire, let's say, that entire tunnel or that entire space. And when we do that, we naturally introduce some coefficients which are associated to the Chebyshev polynomials. And the shape and the size of the corridor will depend on how those coefficients are defined. So the question is, how do we come up with the coefficients that we want? So to do that, we designed a volume maximization problem. And what this would do is this would find the optimal coefficients of the Chebyshev polynomials that would inflate the corridor to occupy the entire free space. And not only we designed that, let's say, optimization problem, but that optimization problem ended up being a convex optimization problem, which we can very efficiently and very reliably solve. I'll not get too much into the details here, but the idea is that this convex optimization problem in the original form was a semi-definite program, which is the most difficult convex problem to be solved. And we found a tight relaxation, so an equal representation, which was a linear program. And this allowed us to solve these problems at 50 Hertz. So basically, we have the capacity to generate these corridors at very high rates in real time. So this is kind of the method that we came up with in order to generate these corridors, these environments. Let me show you some examples of how this works. So the first thing we did is we sanity checked our ideas. So intuitively, we've said that the corridors are represented by polynomials. So the higher the degree of the polynomial, the more expressive the corridor is, the more freedoms we've got to somehow maximize the volume of the corridor. And we expected this, but we wanted to validate this. So we created this kind of like synthetic example where we generated a corridor, let's say, for multiple degrees of polynomial for the same environment. And you see here that a low degree of polynomial somehow doesn't have enough freedom to really adapt to the entire environment. And as soon as we crank this up and we increase the degree of the polynomial, it becomes way more expressive and it can really represent the entire environment. And we did this for multiple polynomial degrees, and we could verify that a higher degree associates to a larger corridor volume. So that makes sense. We validated it through our, let's say, toy example, synthetic toy example, and then we were ready to move this to a real world test scenario. So we tested this in an autonomous driving case study, specifically in the Kitty dataset. And we took this example or this specific instance of the Kitty dataset because it's pretty interesting. It's a car is located in a roundabout and it has a bifurcation. So it has two potential lanes, left and right. And we generated corridors for each of the options. And you see that these corridors are smooth. They are, I mean, you cannot see that, but they've got a continuous gradient, so we can get their gradients. They properly adapt to every single agent in the road, so they encompass the entire width of the road. They adapt to the cyclist and the trucks that we see here, and they somehow are extremely rich representation of the available free space. I'm not showing it here because I wanted to keep this talk within the bounds of the time constraints provided by the organizers, but we did a bunch of experiments against the state-of-the-art methods, and we saw that we had the equal or even bigger volumetric capacity than other methods. And we could also see that we had the extra perk of being smooth and continuous, which is not the case for the convex decomposition standard methods out there. So this brings me kind of to the end of this third point. And here, if you would have to, let's say, remember one thing, is that what we've done is we've come up with an environment representation that is extremely lightweight and extremely rich in the sense that it can fully represent the available free space. So after all these ramblings from my side, if we get back to our original question, how can we embrace egocentricity in autonomous decision making? I believe that we've provided the necessary ingredients. So firstly, we've provided a generalization of the spatial projection to any dynamical system and to any environment. And this is also applicable regardless of the underlying adaptive. Second, we've also talked how to choose the most suitable adaptive frame so that we can use these projections. And third, we've somehow covered how to represent the environment so that we can navigate freely while having no sacrifices in the environmental representation. So hopefully I've convinced you that through these three ingredients, we have somehow addressed the main limitations and we are able to tackle other problems within robotics beyond the specific ones that I've been showing. So this brings me to the last slide of the talk, where I want to somehow maybe think a little bit in a very brief way about the applicability or usefulness of what we've presented. So as I said, I genuinely believe that this kind of generalizes and provides the tools required for applying egocentricity in any robotics problem. And kind of to give you a glimpse into this, I want to talk about some of the examples that benefited from this framework or from these ideas. These are different projects that where I've used these egocentric approaches in my own work with some collaborators. And somehow I hope that with this I can give you like a glimpse into what could be possible. So on the one hand, we use this for developing low-level controllers for pose control, specifically for doing pose following with dual quaternions. And here some of the tools that we've mentioned came especially handy. We also use this to design motion planning algorithms that could exploit different topologies for any dynamical system in a very interesting way. And here also, some of the things that I've been mentioning were key. And finally, here, in collaboration with Rudy, the organizer of this seminar, we also designed application-oriented pipeline where we were able to have a controller that would transport a slush-free, could transport some liquids with robotic manipulators without any sloshing. And this was more of an application-oriented case study. And all these three, like spanning from theory up to applications, somehow benefited from these tools. So therefore, I genuinely, in my opinion, believe that this somehow has a very interesting contribution to the community of robotics. So on that note, I will close with my talk. And before I do that, I want to do a small summary. So if you got distracted or I was too boring and you want to have some takeaways from my talk, here you should pay attention. So the idea is we've started identifying that the biology is egocentric and robotics is allocentric, and there is somehow a need to embed some of the concepts from egocentricity into robotics. We've sanity checked this statement or this hypothesis through tunnel following, just as a simple case study to make sure that it is worth going down this rabbit hole. Finally, we've laid out the main ingredients that would allow us to somehow apply egocentric decision making in any robotic setup, regardless of the underlying problem. And we've closed by very briefly mentioning the potential applications that where this could be useful. So this brings me officially to the end. Thank you very much for those that were able to follow my explanations and to attend the talk. Some of the thoughts that I've been talking about are summarized in a publication that currently is under review, and you've got the QR code to the website here and also the QR code to the paper in here. And if you are interested, of course, we can have a chat now, or feel free just to send me an email and I'll be glad to follow on that. So on that note, thank you very much.
Thank you. Thank you so much, John. That was really insightful. I think now would be a good time. If anyone has questions, please feel free to either unmute or drop it in the chat, and we'll be happy to kind of take questions now.
Maybe I can start, John. Thank you for the wonderful talk. I think it was great listening to all the different questions and how you have presented everything very, very clean. I was thinking, how do you, in this whole framework or pipeline, when you deploy it on the systems, how would you ensure safety, like guarantees on safety? Is there a possibility to have that kind of a stuff here?
Right. Yes, with a small asterisk, right? So let me explain this. Maybe it's easier if I just do this. Let me pop up. Yeah, maybe let me pop up this slide. So safety. Let me explain the small asterisk, and assuming that that's the asterisk, I will answer your question. So if we assume that the sensor data we've got and somehow the environment representation that we've got is somehow accurate, or we've got uncertainty bounds on that, so we know how the environment is defined, we can construct these tunnels or the corridors that I've mentioned at the end, right? And if we assume that those corridors or those tunnels are compliant with the sensor data, which we assume that is valid, which is a big if for like systems application oriented people, if we assume that, then we definitely can guarantee safety. And that's a bit the entire idea of embracing egocentricity, is that it gives you two main benefits. The first one is that you have the capacity to somehow fully exploit your tunnel, and in that way you can be optimal and you can define optimality as you want. But in the second is that you know that everything that happens within that tunnel, you know everything that happens within that corridor, it's safe. Asterisk, as long as those tunnels are properly defined according to the sensor data. But the idea here is that you've got access to the space. Let me go down here. So here, the spatial coordinates, so we are operating in this domain, you've got explicit access to the orthogonal components, right? So safety boils down to constraining these orthogonal components to the cross-section of your tunnel or your corridor. So if we assume that the sensor data is correct and the reconstruction of the tunnel is correct, then 100% you can assume or you can guarantee safety. Then also this goes down to, okay, depends on how you solve the actual control problem, right? Here we provided a set of tools, right? So for example, if you do an NMPC, NMPCs imply solving non-convex problems, and solving non-convex problems, you have to be a bit brave to claim safety guarantees on that, right? So you would have to reformulate this as a convex problem. So the safety guarantee thing would be depending on how you use this to somehow formulate the actual controller or the actual planner. But you do have that environment representation, which is definitely a way to get to that safety. And that's kind of like the point of it.
Mm-hmm.
I don't know if I answered your question.
Yeah, no, sure, yeah. I mean, so I think I was more, this is what essentially I wanted to ask. So if you have these spatial coordinates, can you restrict them somehow and with guarantees that they never go outside your
exactly
your corridor? Because that would be basically
exactly. So honestly, that's the entire deal of this, and maybe this is the better plot for explaining this, and that's the entire point. So with the spatial coordinates, you've got the progress along the path, and you can see that's like amazing, because you can say if you want to go fast, you just build a controller for the progress along the path, and then you've got the orthogonal distance. So in a spiritual sense, all this stuff is you should leave the orthogonal distance free from your cost function, and you should just constrain it in your in your constraints. And by just somehow saying do whatever you want to do with the progress, but everything you do needs to be within the constrained orthogonal distance, and those constrained orthogonal distances have to be inside the corridors.
Okay.
The idea is that if you operate in the XYZ coordinates, you cannot do that because you don't have the orthogonal distance, right? So that's it. That's the entire point of it. That's a bit the spirit that this kind of works follow. Maybe I should have highlighted that a bit better. I think that was an excellent question.
Yeah, thanks.
I have one more question. Thanks. I was curious, how would you incorporate like strategic decision making? So you talked about egocentric decision making, but if you have like two agents that are interacting with each other, how do
Right.
we incorporate like the nature of
Right.
strategic, yeah.
Right. That's an excellent question. Thank you. I mean, that's an excellent question, which it's an obvious follow-up somehow, right? Or not obvious, but it's an excellent question. And I would maybe rephrase the question if I got your question properly. It's
Mhm.
what you're asking is how do you actually do proper planning with this, right?
Yeah,
Because
high
what we
level
are doing
planning.
is like everything I've talked about, it's a single corridor, right? And 100% I agree with this. And this is somehow what I would like to do as a following thing. And here there are very interesting takes. So the idea is that this is within the scope or the mindset of continuous optimization. We've got an environment representation, which is a tunnel, and we optimize over this, and somehow we get a dynamically feasible trajectory. But then there is a meta question, which is like you gotta have a plan, or you gotta plan on top of that, right? So, and so far historically, these have been like two different layers. Historically, you had like the search-based planners, which kind of did their own thing. They would do like a grid search thing, and then you would have the continuous control side or the continuous optimization side, which would get you these trajectories. But probably you see where I'm going. In the last few years with GCS, this has a little bit changed, right? Where now we've got the capacity to kind of like combine this search, like grid-based or discrete-based search with the continuous optimization pipeline. So what I could see here is an interesting intersection of really exploiting the volumetric knowledge that we've got from the corridors and all the spatial privileged information that we've got from somehow projecting ourselves and combining that with a planning approach. I think it's something I'm honestly super excited about, and I've been pitching to a bunch of people for a while. And this could be maybe applied to your question of strategic decision making if you've got multiple agents or something like that, which I see more of a broader question of how do you combine it with discrete search. I don't know if I answered your question.
Yeah, that's very interesting. Just to clarify, when you meant GCS, do you mean graph of convex
Yeah,
sets, those
sorry.
approaches?
Yeah, that's what I meant. Yeah.
Okay.
Yeah.
Yeah, that's the direction I'm looking into right now. So that's definitely very interesting, very relevant.
100%, yeah. And there is another take to this, which, I mean, I have had different feedbacks from different people, which is that also GCS kind of the actual, but some people might disagree with this, but the actual bottleneck is that it needs a convex decomposition method to somehow then optimize over.
Mhm.
And there is a flip side to this, which is that I didn't get into this because somehow, but these corridor generation methods directly compete with convex decomposition. It's an alternative way that instead of decomposing the space, you just generate one corridor. So something that could, like a possible hypothesis here would be, instead of having like 10 decomposed convex sets, maybe you can have 3 corridors or 2 corridors as convex representations. And that could also lead to interesting accelerations within GCS. Once again, I haven't properly thought about this. I have had different feedbacks from different people, but this is also an alternative side to the same comment. Yeah.
Interesting. Thanks. I'll follow up with you later, probably, or email. I have some suggestion.
Super happy to do that, Karan. Thank you.
All right. I could also just quickly check what comes next for this research. Are you looking at more applications where you can kind of take this and test out in different settings, or are you looking at other ways of parameterizations, or yeah?
Right. So there are two. That's an excellent question. There are two ways I would like to answer to that question. So the first one is the direct answer that some people might expect, somehow how I see this evolving. The first thing is a bit with what we've been talking with Karan. I genuinely have been thinking about these GCS ideas and somehow beyond GCS, kind of taking this to the planning approach, because I think that's where some of the cool problems are really, and somehow combining the planning side with the actual continuous optimization side, which has been covered here. So that's one, like kind of like extrapolating or getting to the higher level. And the other one is also, let's say maybe I can use this also to advertise this, because I'm genuinely looking for someone that would be willing to extend this like more in let's say it's more of an application oriented thing of actually extending this corridor generation method in a sense that could be immediately applicable from RGB cameras. Currently it requires LiDAR, so it requires point clouds, And the implementation we had, it's all right, but it could be improved. So it would be super nice. And I think the community would definitely approach from having like a ROS package that you just plug in your camera and can just shoot a bunch of tunnels and corridors. I think that would be amazing. And I think it's doable. It's a lot of software work, but I think the option is there. So that's one side of the answer of the immediate extensions I see to this. But then the other one is like kind of acknowledging that the world has changed a little bit in the sense that basically navigation, it's a problem that it's starting to become, I should be careful here. Navigation, it's a problem that we are getting a lot of solutions and we know how to do properly. And little by little, I'm getting different interests in different problems where more open questions are still to be answered. I'll not be more explicit than that, but I'm still super happy to continue with this. But I do think there are also other pressing issues that we should address more in a fundamental level.
That's exciting to hear. Yeah, that kind of then brings us to the end of today. Thank you so much again, Jon, for your time and the fantastic talk.
Thank you very much for inviting me. This was great. And thank you for all the questions.
Thanks, Nate.